Welcome to Hired in IT. Our mission is simple: help you build the skills that employers actually want. Whether you're trying to land your first IT job, switch careers, earn a promotion, or increase your salary, we're here to help. Every video is thoroughly researched and designed to make complex IT topics easy to understand. If there's an IT topic you'd like us to cover, leave a comment below. We may turn your suggestion into our next video. Turning IT knowledge into career opportunities. Imagine you're logging into your bank's website. You type the correct web address, and your browser begins setting up an encrypted connection. Unknown to you, an attacker sitting on the same public Wi-Fi intercepts the communication and tries to replace the bank's public key with one they control. If your browser simply accepted any public key it received, the attacker could read everything you send, even though the connection appears encrypted. Encryption alone isn't enough. Before encryption begins, your browser has to answer one critical question. How do I know this public key really belongs to my bank? That's the problem Public Key Infrastructure, PKI, was designed to solve. Last episode, we demystified AES, RSA, and TLS, all the math that scrambles your data. But encryption alone can't tell you if you're really talking to your bank or a fake Wi-Fi hotspot. That question, who is on the other end, is why certificates and PKI exist. By the end of this video, you'll be able to trace a certificate chain to verify who's behind a padlock, generate your own certificate signing request, and inspect an X.509 certificates fields to catch expirations and forgeries before they become problems. Here's what you'll be able to do when we wrap. First, trace the chain of trust, from the padlock in your address bar up to a root certificate sitting in a vault. Second, fire up a terminal and generate a real CSR just like a sysadmin would. And third, pop open any website certificate details and know immediately if something's off. No fluff, just skills that show up on a job interview. Alice wants to send Bob an encrypted message, so she shares her public key. But Eve, sitting in the middle, intercepts that key and swaps it with one she controls. Now Bob encrypts data with Eve's key. Eve decrypts it, reads the secret, re-encrypts it with Alice's real key, and forwards it. Neither Alice nor Bob realizes anything is wrong. Encryption was working perfectly. The problem was never the math. It was that nobody could prove the key actually belonged to Alice. So what's the fix? You need something that says, "This public key really belongs to Alice and I vouch for it." That something is a digital certificate. Think of it as a digital passport. A passport binds a photo and name to a real person, and it's issued by a government you trust. A certificate binds a public key to an identity, a person, a server, a device, and it's signed by a third party called a certificate authority. Just like a border agent checks a passport stamp, your browser checks that digital signature. If a certificate is a passport, PKI is the entire system that issues, renews, revokes, and checks them, at scale. Public key infrastructure is the mix of hardware, software, policies, and people that keeps the whole trust framework running. It's not a single protocol. It's the ecosystem that makes it possible for your browser to verify millions of websites every second without you ever thinking about it. Without PKI, every website would have to prove its identity from scratch, and the internet would grind to a halt. Several components work together to make PKI possible. First is the Certificate Authority, or CA. Think of it as the trusted organization that issues digital certificates. Next is the Registration Authority, or RA. Before a certificate is issued, the RA verifies that the requester really owns the identity they're claiming. The subscriber is the person, server, or device receiving the certificate. The relying party is the browser, application, or user that checks the certificate before deciding whether to trust it. Finally, certificates and revocation information are published, so systems can verify that certificates remain valid. Each component has a different responsibility, but together they create the chain of trust that secures modern communications. The certificate authority is the foundation. The very top of the food chain is the root CA. It creates a self-signed root certificate. There's nobody above it to vouch for it, so it vouches for itself. Because of that, its private key is guarded like a crown jewel, stored offline, often in a physical hardware security module. Browsers and operating systems come preloaded with a list of trusted root CAs. If that root key gets stolen, an attacker could issue valid certificates for any website, and every browser would trust them. That's why these keys are air-gapped and protected with procedures you'd expect at a nuclear facility. In large organizations, the CA doesn't talk to every person who wants a certificate. Instead, a registration authority, the RA, acts as the gatekeeper. The RA checks your driver's license, your domain control, your business registration, whatever level of assurance the certificate demands. Only after the RA says, "This identity checks out," does the CA issue the signed certificate. Without this split, anyone could claim to be Google.com and get a valid certificate. That's the whole reason we don't hand out certs at the door. Somebody has to verify the person behind the request first. Every certificate follows the X509 standard, a digital document with specific fields. When you open one in a browser, here's what you'll see. The subject, like www.bank.com. The issuer, which is the CA that signed it. A validity window, not before and not after. And certificates are instantly invalid outside that range. The public key itself, the signature algorithm the CA used, a unique serial number, and any extensions like what the key is allowed to do or extra domain names it covers. If any one of these fields looks off, a wrong issuer, a weird expiration date, you've spotted trouble. That's exactly the skill you'll practice at the end of this video. Everything we've discussed so far can be shared publicly, except one thing: the private key. Think of it as the master key to your digital identity. If you're running a secure website and someone steals your server's private key, they may be able to impersonate that server until the certificate is revoked. If it's a code signing certificate, they could sign software so it appears to come from a trusted publisher. If it's an email certificate, they could impersonate the sender or decrypt protected email intended for that identity. The exact impact depends on what the certificate was created for, but the rule never changes. The private key must always remain private. Protect it with strong access controls, or even better, a hardware security module for highly sensitive environments. Recall Part 7. We used RSA to encrypt a symmetric key and assign a digital signature. The private key is the one piece that must stay secret. Now, imagine someone steals that. What's the worst that could happen? Trust in PKI flows downward. At the top, a root CA, a self-signed certificate your browser already trusts. The root signs an intermediate CA, delegating authority. Then the intermediate signs the end entity certificate your web server presents. When you visit a site, your browser walks this chain from leaf to root, checking every signature. If any hop fails, maybe the intermediate's signature doesn't verify or a certificate has expired, you get that padlock with a red line. The chain limits damage. Compromise an intermediate and you only need to revoke certificates below it, not the entire root. Your browser is the most paranoid auditor on the planet. It checks that each certificate in the chain was signed by a trusted CA, hasn't expired, and hasn't been revoked, consulting a CRL or OCSP responder for the latest status. If everything passes, you get the padlock. But here's the beginner trap. If you see an untrusted issuer warning, don't click through. Your browser is telling you it can't verify the signer. That's the textbook red flag of a man-in-the-middle attack, not a minor glitch. The intermediate CA sits between root and leaf, issuing certificates daily. It's online but heavily protected. If it's compromised, only certificates below it need revoking, not the root. Now, compare the extremes. Root CAs are fortresses, air-gapped, in hardware security modules, valid for decades. Leaf certificates are typically short-lived. Some organizations rotate them every few months. To limit exposure, and rotating them effectively rotates the key pair as well. When you see a website certificate with a short expiration window, that's by design. Meet Dave. He's a sysadmin who just got laid off. Before he cleared his desk, he exported the SSL certificate for the internal finance portal, private key and all. That certificate is still valid, signed by the corporate CA, and trusted by every browser inside the company. For the next 6 months, Dave can sit in a coffee shop, intercept traffic to the payroll system, and decrypt it. He's a man in the middle with a valid passport. This is why revocation exists. You need a way to kill a certificate before it expires. Otherwise, your PKI is a house with a key that never stops working. The original solution to Dave's problem: certificate revocation lists. The CA maintains a digitally signed list of revoked certificate serial numbers and publishes it. Clients download this list, often hundreds of megabytes, and check certificates against it. But there's a dangerous latency problem. CRLs are updated on a schedule, so a freshly revoked certificate may still appear valid until the client fetches the next version. During that gap, Dave's certificate still works. This is why relying solely on CRLs leaves a window of risk. Certificate revocation lists solved one problem, but created another. Browsers had to download large lists that might already be out of date. To provide faster status checks, the industry introduced the Online Certificate Status Protocol, or OCSP. Instead of downloading an entire revocation list, the browser asks the CA a simple question: is this certificate still valid? The server replies with one of 3 answers: good, revoked, unknown. This provides much more up-to-date information, but it introduces another consideration. Every direct OCSP request can reveal which website a browser is visiting. To reduce both latency and privacy concerns, many websites now use OCSP stapling, where the server includes a recently signed OCSP response during the TLS handshake so the browser doesn't need to contact the CA directly. CRL is like checking a blacklist posted on a public board. Bulky, updated on a schedule, but no one learns what you looked at. OCSP is like phoning the CA every time. Instant answer, but the CA now knows every certificate you've asked about. One modern approach to address the privacy concern is OCSP stapling. The web server fetches its own OCSP response ahead of time and includes it in the TLS handshake. That way, the client gets revocation status without ever contacting the CA directly, reducing the privacy exposure Here's the full life cycle. You start by generating a public-private key pair. You bundle the public key and identity details into a certificate signing request, the CSR, and send it to a CA. The CA validates your identity, signs the certificate, and returns it. You install that signed certificate on your server, and TLS is ready. But it doesn't last forever. You must renew before the expiration date, or everything breaks. And if the private key ever leaks, you revoke the certificate immediately, publishing its serial number so no one trusts it again. You generate a CSR, send it off to a certificate authority, and get back a shiny new certificate. So, who actually signed that document? The CA, using its own private key. The issuer field on the certificate tells you exactly which CA did the signing. This is the same asymmetric crypto from Part 7. The CA uses its private key to sign, and your browser uses the CA's public key from the CA's own certificate to verify. If the signature doesn't match, that certificate is invalid. Let's generate a real certificate signing request using OpenSSL. This single command creates a new key pair and the CSR in one step. The new key flag tells OpenSSL to generate a fresh 2048-bit RSA key. The keyout flag names the private key file, outnames the CSR file, and nodes skips, encrypting the private key, handy for scripts, but a security risk if the file ever leaks. In production, consider omitting nodes and protecting the key with a passphrase. After the CA issues your certificate, what does it actually look like? It usually arrives as a PEM file, plain text wrapped between begin and end lines. The base 64 block in the middle bundles the certificate's essential information, identity, public key, and validity dates, plus the CA's signature. PEM is the most common format, though you may also encounter DER, a binary equivalent. To inspect a PEM certificate's details, use the OpenSSL X509 command with the text and no out flags to display every field in readable text. Once you have a certificate file, you need to make it available to the system. In Windows, you can use the Certificate Import Wizard to place the certificate into the appropriate store. Choose the personal store for most server certificates. If the file includes a private key, you'll be prompted for its password. That's the last line of defense before the key lands in secure storage. Once the wizard finishes, services such as IIS can reference the certificate. You've got your certificate installed and the browser padlock appears. Now here's the mistake that leads to compromise again and again, letting the private key file end up in a public repo. The certificate file is public. That's fine. The private key is not. It's the secret that proves you are that server. If an attacker grabs it, they can impersonate your site and decrypt TLS sessions. Treat private keys like passwords, rotate them regularly, and never let them leave your control. That padlock in your address bar is the end result of PKI working perfectly. When you visit an HTTPS site, the server sends its leaf certificate. Your browser walks up the certificate chain, checking signatures against trusted routes, verifying expiry dates, and checking revocation status. If everything passes, the browser uses the public key inside the certificate to help negotiate an encrypted session. The padlock means two things. The connection is encrypted, and the server's identity is verified. You really are talking to your bank, not a hacker in a coffee shop. When you download an installer for your favorite app, how do you know it hasn't been backdoored? A code signing certificate answers that. The developer uses it to digitally sign the executable. When you run it, Windows and Mac OS check that the signature matches the publisher, and that the file hasn't been modified. Without a valid signature, you'll typically see warnings that can deter users. A lot of malware campaigns start with a stolen code signing key. It turns a fake installer into something that looks legitimate. That's why code signing keys are guarded almost as carefully as root CA keys. SMIME certificates bring PKI directly into your inbox. Once you install an SMIME cert in Outlook or Thunderbird, you can digitally sign an email. That adds a ribbon icon proving the message really came from you and wasn't altered in transit. Encrypting an email locks it so only the recipient's private key can unlock it. Not even the email provider can read the body. This is widely used wherever email confidentiality and non-repudiation matter. Getting started. Obtain a certificate, import it into your client, and look for the Sign and Encrypt buttons. In a smart factory, every sensor and actuator gets its own certificate, just like a server does. These are issued by an internal certificate authority. When a temperature sensor needs to send data to an assembly line actuator, they don't just trust each other blindly. They perform a mutual TLS handshake. Both devices present their certificates, and both verify the other against the trusted root. A rogue device plugged into the network can't inject false readings because it doesn't have a valid certificate. This is zero trust at the hardware level, and it's becoming the baseline for industrial IoT security. Managing one certificate isn't difficult. Managing thousands across web servers, cloud services, containers, APIs, and IoT devices is a completely different challenge. Certificates expire. Private keys must be protected. Compromised certificates must be revoked quickly. Renewals have to happen before services stop working. That's why enterprises rely on certificate lifecycle management platforms. Solutions such as Azure Key Vault, HashiCorp Vault, Cert Manager for Kubernetes, and Venafi help automate certificate issuance, renewal, monitoring, and revocation. As organizations adopt zero trust and cloud-native architectures, automation isn't just convenient, it's essential. Now the big fork in the road: who actually issues the certificates? On the left, the Public Certificate Authority, companies like DigiCert or the free Let's Encrypt. Their root certificates are preloaded in major operating systems and browsers, which is why your site gets a padlock with zero extra steps from the user. On the right, a private CA. You spin up your own, maybe using Windows Server ADCS or a few OpenSSL commands, and become your own DigiCert. The catch? Every client that talks to your internal services has to first trust your homegrown root. It's a bit of legwork, but you pay nothing per certificate and get total control. Many enterprises run both. Let's Encrypt for public marketing sites and an internal CA for thousands of devices behind the firewall. Know which approach fits your situation and you're already thinking like a PKI architect. PKI is one of those technologies that quietly powers almost every secure system you'll work with. Whether you're supporting Microsoft Active Directory certificate services, securing web applications, managing Azure Key Vault, implementing zero trust, or troubleshooting TLS errors, you'll encounter certificates throughout your IT career. That's why employers value professionals who understand not only how certificates work, but also how to deploy, renew, troubleshoot, and automate them. PKI knowledge supports careers in system administration, cloud engineering, cybersecurity, DevSecOps, identity and access management, and security architecture. As you gain experience in these areas, PKI becomes a valuable skill that complements many higher-level security and cloud roles. Here's a trap I watch beginners walk into every week. You need HTTPS fast for an internal demo. So you run one OpenSSL command and generate a self-signed certificate. On your machine it works, because you manually added it to the trust store. Then your manager hits that same URL from a phone and sees a giant red screen. Your connection is not private. Attackers might be trying to steal your information. That's an instant credibility killer. A self-signed cert is like crafting your own passport at home and wondering why the airport rejects it. There's zero identity verification. I can create a self-signed cert for Google.com right this second, and your browser will scream. The real-world rule. Self-signed is fine for local development or sealed-off internal labs where you push your cert onto every client. Anything public demands a CA-issued certificate. Even internally, it's cleaner to set up a proper private CA. Trust one root, not 30 separate self-signed certificates you'll forget to renew. A major cloud provider once suffered a massive authentication outage because of a single expired TLS certificate. No attack, just a calendar miss. Many certificate authorities now issue certificates with a maximum 1-year validity, and Let's Encrypt uses 90-day certificates to encourage automation. That forces you to build a system. A calendar is your first line of defense. Reminders at 90, 60, and 30 days before expiration. Better yet, automate. Tools like CertBot renew. Let's Encrypt certificates silently at the background, and cloud key management services can auto-renew and redeploy for you. The goal is to make certificate expiry a non-event, not a 3 a.m. panic call. Miss this, and your shiny PKI becomes the outage headline. Don't be that story. Let's tie it all together. This wasn't just theory. You now understand the engine that secures the internet. First, PKI solves the fundamental problem we opened with. How do you know a public key actually belongs to the person or server claiming it? Signed certificates. Second, the chain of trust ensures no weak link can fake an identity, all the way up to a root you already trust. Third, and here's the career piece. You can now generate a CSR, talk about certificate revocation, and explain lifecycle automation in an interview. Those are skills that separate the help desk resetter from the security engineer hiring manager's chase. Lock those 3 takeaways in, and you're ready for whatever certificate scenario comes next. Ready to turn knowledge into muscle memory. In the description, I've linked Let's Encrypt. Grab a free certificate for a real domain today. I also recommend Small Steps Everything PKI Guide, the most readable deep dive you'll find, and it's free. Grab the OpenSSL cheat sheet while you're there. This week, your challenge: pick a test domain, even a local one, and generate a real CSR using the OpenSSL rec command. That one command is the on-ramp to every PKI rollout there. The community in the comments is sharing their setups and troubleshooting together. Jump in and post yours. Let's make this practical. Next episode, we're pulling back the curtain on the TLS handshake. Exactly what happens in the fraction of a second when you see the padlock. You'll watch client hello, server hello, certificate exchange, and key agreement play out step by step. If you thought PKI was powerful, wait until you see how that chain of trust gets used to create the encrypted tunnel protecting every credit card number and login. Same IT Fundamentals Masterclass, next part. I'll see you there. If this clicked for you, do the usual. Hit subscribe and ring the bell so the TLS deep dive lands in your feed next week. Drop a comment. What certification are you working towards? Security Plus, PSI Plus, CCSP. I read every one, and it helps me build the content you actually need. The playlist continues. Keep growing, keep securing, and I'll catch you in the next one. Remember, careers aren't built by watching videos. They're built by applying what you learn. Pick one thing from today's lesson, build it, document it, and share it. That's how you get hired. Thanks for watching Hired in IT, where we're turning IT knowledge into career opportunities.